In this video, we're going to look at a synthesis reaction. The word synthesis means to combine, and that's exactly what we're doing in a synthesis reaction. You'll have two or more small elements that join to make a compound, kind of like sodium reacting with chlorine to produce sodium chloride. Or you could have small compounds that join to make a larger compound, like water reacting with carbon dioxide, forming hydrogen carbonate. Now, the trick here is that you will always have just one product. You could have two or more. You could have 2, 3, 4, 5, 6, 7, 10 reactants, but they'll join to make one product. Now, that one product is more stable than the original reactants. We've looked at sodium chloride in the lab. Earlier this year, we tried to break the sodium chloride bond by adding heat. And I don't think anyone was able to break apart sodium chloride. It's a very, very stable bond. If something is very stable, that means it's at a low energy level. The sodium metal is highly reactive, and so is chlorine gas. But when they form the sodium chloride bond, it's a very stable bond, which means that energy was released. These synthesis reactions are often exothermic. When I form that stable bond, we release energy in the form of heat or light. When something is more stable, it's always associated with lower energy levels. So energy must have been released. When we predict products of synthesis reactions, we'll just have simple elements that join to make one compound. So for example, if I want to write the chemical equation for the reaction of magnesium metal and oxygen gas, I'm going to write my symbols. Magnesium, Mg, is not diatomic, but oxygen gas is, O2. So we join these together, we're going to make magnesium oxide, right? You betcha. So when you form your product, join the symbols first. Combine element symbols first. Subscripts do not get a free ride to the product side. So for example, oxygen was diatomic only in its elemental form. But now if I have a compound with oxygen, I need to write the formula by balancing charge. So magnesium is +2, oxygen is -2, and that sucker's neutral. The most common mistake is people will read this as Mg plus O2 forms MgO2. I mean, come on, we know that doesn't exist. Sad face. That's not the formula of magnesium oxide. The 2 is only present on the reactant side when oxygen was diatomic by itself. Where each oxygen has 6 valence electrons, they need 8, so they share in a double bond. O2 is very stable. But in a compound, we have to check the charges. Okay, now I get it. I need 2 oxygen, but we can balance with a coefficient. 2 oxygen, 2 magnesium, game over, right? Now we probably should put the phase symbols in. Magnesium metal is a solid. Oxygen is a gas. Now we're going to run this reaction in the lab, and it's really awesome. It looks on paper like it could be kind of boring, but you're going to love it. It gives off tons of energy. You'll notice after you burn this piece of magnesium metal, there's like a white powder, like a white residue that'll be left on your tongs. That white solid is the magnesium oxide. So in the lab, when I run these reactions, I can experience my products, and that might help me get the phase symbol. Wow, what's this white crumbly solid that's left over from burning magnesium metal in oxygen. Now, later on, I'll also show you another chart that you can use to find phase symbols if by chance it's something that you're not familiar with or you're not running the reaction in the lab. Done. You're going to love this reaction. It's really easy. Take a piece of magnesium, burn it in the presence of oxygen. It's not a true combustion because we're not forming carbon dioxide and water. It's a synthesis where the magnesium joins with oxygen in the air. And it does give off tons of energy. All right, the equation for the reaction of sodium metal and nitrogen gas. Sodium is not diatomic, but nitrogen gas is. So when I make my product, it should be sodium nitride. Sodium plus nitrogen makes sodium nitride. So I get the symbols together and check the charges on the periodic table. +1, -3. Whoa, I'm going to need 3 sodium. And again, I understand that this is not neutral. Or say it's not balanced. My formula is neutral now. Now, my gut is to put a 3 in front of the sodium on the reactant side, but then I just noticed that eventually I'm going to need 2 nitrogen. So if I put the 2 in front to get the 2 nitrogen, eventually I'm going to have 6 sodium. 6 sodium, 2 nitrogen, excellent. Sodium metal is a solid, nitrogen is a gas. Sodium nitride, kind of the same, it's like a white crumbly solid. Now don't freak out about the phase symbols, because again, we're either going to run these in the lab so you can see the phase of your products, or later on, I will show you a chart that you can use to find phase symbols. These are the typical synthesis reactions that we'll run. I mean, I would be able to identify something like this as synthesis. It's small compounds that join to form one larger compound. But most of the ones that we'll run will just be individual elements that join and make the compound.